Our planet is an incredibly dynamic and sometimes literally violent system. I mean, over its 4.6 billion year history, Earth has undergone some truly dramatic transformations. But honestly, none are quite as awe-inspiring or, let's be real, as terrifying as the periods when it completely froze over. We're talking about an entire planet encased in a thick shell of ice, fundamentally altering the chemistry of the oceans, the composition of the atmosphere. Now, you might be wondering, how could a frozen, desolate planet with ice sheets stretching from the poles all the way down to the tropics lead to us? It sounds completely counterintuitive, right? It looks like a dead world. It looks like the absolute end of the line for biology. But as we unpack the incredible data hidden in ancient rocks, we're going to uncover a profound paradox. These complete planetary deep freezes weren't just mass extinction events. Actually, they were the ultimate crucibles. They were the intense, brutal catalysts that forced simple life forms into evolutionary bottlenecks, paving the exact path for the complex, multicellular existence we enjoy today. Section 1. 2 Snowball Earths. Okay, let's map out exactly when our planet turned into a giant snowball, where sea ice and continental glaciers literally reached all the way to the equator. Geologists have identified two primary eras. The first was the Huronian glaciation, roughly 2.4 billion years ago. Fast forward deep into the Neoproterozoic era, and we hit a massive double whammy. The Sturton glaciation, starting about 720 million years ago, followed relatively closely by the Marinoan glaciation, around 645 million years ago. Even though they're separated by billions of years, they share incredible similarities in how they completely overrode the planet's thermostat.
Section 2. Causes of Snowball Earth.
So what on Earth could cause a thriving, watery planet to just freeze solid? A catastrophe of this magnitude requires a total failure of the planet's climate systems. And what we see in the geological record is the perfect storm of cooling. Early on, the sun was about 20 to 25% fainter than it is today. On top of that, you had tectonic plates shifting all the continents toward the hot, wet equator. This continental placement massively accelerated a chemical process called silicate weathering, which acts like a sponge, sucking carbon dioxide right out of the air. Combine that with huge lulls in volcanic activity, and you effectively strip the planet of its warming blanket. To really understand the biological shifts here, we have to look at the atmosphere during that first freeze, the Huronian glaciation, 2.4 billion years ago. Back then, because the sun was so weak, the Earth relied heavily on a thick blanket of methane, which is a super potent greenhouse gas, to stay warm. But then, early cyanobacteria evolved and started pumping out something highly toxic to that environment, free oxygen. This sparked the Great Oxidation Event. The newly abundant oxygen reacted with the atmospheric methane, destroying it and replacing it with carbon dioxide. Because CO2 is a much, much weaker greenhouse gas than methane, the planet's insulation was suddenly destroyed, plunging global temperatures into an absolute freefall. And this brilliantly illustrates the geological trigger for the later Sturtian freeze. What we're looking at here is the Franklin Large Igneous Province. About 719 million years ago, a massive volcanic event poured flood basalts across an area near the equator. Now, normally volcanoes warm the Earth, right? But this fresh basaltic rock is highly reactive. Sitting right at the wet, rainy equator, it underwent intense chemical weathering. So instead of warming the planet, this massive new rock formation acted like a gigantic CO2 vacuum, draining the atmosphere of greenhouse gases and kicking off the longest deep freeze in planetary history. Now, you might be asking, how do we actually know the ice made it all the way to the equator? Well, the smoking gun is a specific type of rock called diamectite. This is essentially a chaotic jumble of mixed-sized rock fragments and boulders that are bulldozed and deposited by moving glaciers. But the key here isn't just that we find diamectite, it's where we find it. Using paleomagnetic data, which cleverly tells us where a rock was located when it originally formed, geologists have proven that these glacial deposits were laid down in ancient tropical, equatorial latitudes. Glaciers at the equator mean one thing: a planet completely covered in ice.
Section 3. Greenhouse gases ending ice ages.
Okay, so once Earth was covered in this bright white shell of highly reflective ice, bouncing almost all of the sun's energy back into space, how did it ever escape? The answer lies in a dramatic reversal of the carbon cycle. It works through a fascinating loop. Step 1, ice completely covers the continents, which entirely stops that weathering process we mentioned that sucks CO2 out of the air. But step 2, volcanoes don't care about surface ice. They just keep erupting right through it, pumping carbon dioxide into the atmosphere. Step 3, that CO2 accumulates uninterrupted for millions and millions of years. Finally, in step 4, the greenhouse effect becomes so incredibly overpowering that it forces a runaway melting process, breaking the ice's grip on the planet. Section 4. The extreme super greenhouse Earth. Let's see how this builds into an entirely new, deeply terrifying phase. As the ice begins to break apart, the Earth doesn't just, return to a mild, pleasant climate. The immense buildup of CO2 triggers a violent whiplash effect. This whiplash is driven by something called albedo reversal. White ice reflects sunlight, keeping things cold, but the moment that ice starts melting and exposing dark ocean water and dark land masses, those surfaces start absorbing the sun's heat. This extra heat melts more ice, which exposes more dark surfaces, which absorbs more heat. It's a massive, unstoppable positive feedback loop. In the blink of geological time, the reflective shield is gone, leaving the Earth naked beneath a ridiculously thick blanket of carbon dioxide. Now, what's really fascinating when we look at the geological cross-section is the stark, undeniable line it draws. We literally see rock where glacial deposits from the deepest, coldest periods of Earth's history are abruptly, sharply covered by thick layers of completely different rock. There is absolutely no gradual transition here. It goes instantly from extreme freezing cold right into a blistering hot environment. Those sudden overlying rocks are called cap carbonates. These are layers of limestone or dolomite that can be up to 200 meters thick. They are found globally, capping the ancient glacial deposits of both the Cretaceous and Marinoan freezes. In a superheated ocean completely saturated with CO2 and experiencing intense runoff from freshly weathering continents, these carbonates precipitated out of the water incredibly fast. They serve as the ultimate, undeniable physical evidence of the super greenhouse environment that immediately followed Snowball Earth. And we have to remember, this environment was profoundly hostile to life. This toxic thaw wasn't a gentle spring by any means. The early life forms that had just barely survived millions of years locked under ice were suddenly subjected to extreme high temperatures and extreme oceanic acidification from hundreds of times the modern CO2 levels. On top of that, the massive melting of glaciers dumped unfathomable amounts of fresh water into the oceans, which physically separated the ocean into distinct non-mixing layers. This stratification led to widespread euxinia, which basically means the deep ocean was starved of oxygen and choked with highly toxic hydrogen sulfide. Section 5. Promotion of multicellular evolution. Yet, despite being subjected to the most grueling environmental whiplash imaginable, life didn't end. In fact, this sequence of utter planetary devastation acted as a brutal, unparalleled evolutionary crucible, forging the very beginnings of complex life. It's really essential to contrast the two major Neoproterozoic freezes here. The Sturtian Ice Age was grueling, lasting an incredibly long 56 million years. That extended duration, completely starved of oxygen, placed overwhelming stress on simple organisms. But the Mironian Ice Age was much shorter, lasting only about 4 million years. That shorter duration is vital. It was just severe enough to cull the weak and force extreme adaptation, but short enough that it provided a critical window for these new, complex adaptations to survive and eventually thrive when the ice melted. In fact, right in between the grueling Sturtian freeze and the Marinoan freeze, there was a roughly 10 million year interlude of warmer, non-glacial conditions. The geochemical data shows us that during this specific narrow window, biological innovation absolutely exploded. Algae and very early multicellular life, perhaps early sponges, started to rise and dominate the ecosystem. The evolutionary seeds were planted right in the brief calm between the two greatest storms in planetary history. So the crucial point is this: the relentless cycle of being pushed to the brink of freezing death, only to be plunged into a boiling toxic ocean, created an immense evolutionary bottleneck. Only those organisms that mutated, adapted, and learned to cooperate at a cellular level could endure. Snowball Earth didn't just clear the playing field. It violently forced single-celled organisms to band together, jump-starting the morphological diversity that would eventually lead to all complex animals, including us. It's a staggering reality to confront, isn't it? The absolute worst-case climate scenarios imaginable, events that sealed the planet in ice and then choked it with toxic heat, were the exact requirements for complex life to evolve. It really makes you realize that our existence isn't a given. It's the result of unimaginable trials. As you go about your day, consider that paradox. If our complex, intricate existence absolutely relied on the Earth nearly destroying itself twice, what does that reveal about the incredibly fragile yet relentlessly resilient nature of life on our planet right now? Keep that in mind as we continue to understand our ever-changing Earth system.